Alright, in the previous video we introduced the concept of a boundary layer, and we spoke and also introduced terms like inner region, outer region, rescaled variable, and we also mentioned the method of meshed asymptotic expansions. Now let's look at a particular example here. We have got epsilon dy dx plus y equal to x. The initial condition is when x is 0, y is 1, and we're looking for a solution in the domain x greater than 0, x equal to 0 included. Okay, we're going to start by noting that this equation can be solved exactly. This problem can be solved exactly, and the exact solution is as follows. So the exact solution, y equal x minus epsilon plus 1 plus epsilon e to the minus x over epsilon. So that's our exact solution here. Now we're going to start by looking for a solution in the outer region. So we mentioned in the previous video that that this is a solution determined by regular perturbation theory. Okay, so which one is the outer region we are going to determine as part of the solution. So here we're going to look for a solution y equal to y naught plus epsilon y1 plus epsilon squared y2, etc. Now if we substitute this into the given problem and compare coefficients of powers of epsilon, then this is what we're going to get at order epsilon to the power 0. So substitute and compare or balance. So at order 1 or epsilon to the power 0, so then it's going to give us y naught is equal to x. Now so this is our reduced problem. You're going to notice that the original problem is an ODE of first order. This one is actually an algebraic equation, which is a characteristic feature of singular perturbation problems. So as a consequence, this cannot satisfy the given condition. So this cannot satisfy the condition that y equals to 1 when x equals to 0. So this is going to make us to infer that this outer solution, or this solution, is going to be valid in a region away from x equals to 0. So hence the solution must be valid away from x equals to 0, which makes the region away from x equals to 0 our outer region. If we make a sketch of the situation actually, so what we have is y naught is equals to x, gonna be a straight line like this, but then when x equals to 0, solution needs to be y must be equal to 1. So this is telling us that very close to the origin, there's going to be a region where the solution adjusts from the straight line behavior and then adjusts towards y equal to 1. So this is going to be our boundary layer. So we're going to have a boundary layer, or what we have called the inner region, closed to 0, or in the neighborhood of x equals to 0. And then away from x equals to 0 is going to be our outer solution. Now, continuing with our regular perturbation solution, at order epsilon, we are going to have y0 prime plus y1 equal to 0. Now remember, y0 is equal to x, so y0 prime is 1. So this is telling us that actually y1 is going to be -1. And then at order epsilon to the power n, where n is 2 or greater, the equation is going to be pretty similar in structure to this one. But the only difference now is that all these terms here are going to be 0. For instance, y1 prime is 0. So that means y2 is going to be 0. So yn here is going to be 0 for all n 2 and greater. So that means the outer solution is fully determined now. So we have y is equals to x, which is y0, and then y1 is -1, so it's going to be -1 times epsilon, and then all the other terms are 0. So this is our outer solution. All right, so then now we turn into the inner solution. So in the inner region, being the region in the neighborhood of x equals to 0, we are going to introduce a rescaled variable defined as follows: x equal to epsilon to the power alpha xi. Then the dependent variable as well, we're going to rename capital Y. Then by the chain rule, so dy dx is going to be d big Y dxi times dxi dx. This thing is going to give us xi to the power alpha dy dxi. And so the ODE is going to become epsilon to the power 1 minus alpha dy dxi plus y equal to, it's going to be equal to epsilon to the power alpha xi. When x is equal to 0, xi is also 0. So this condition is now going to look like this. Then alpha is determined by what is called a distinguished limit, which we introduced when we looked at singular problems of algebraic equations. So you might want to look at that particular video if you are not familiar with that idea. So here we start balancing terms, and that's how we obtained the That's how we obtain the distinguished limit. So if we balance term 1 and term 3, this tells us that 1 minus alpha must be equal to alpha, those being the powers of epsilon in the respective terms. So this is going to give us alpha is equal to a half. So if alpha is equal to a half, then term 1 is going to be order epsilon to the power a half. Term 2 is going to be order 1, and term 3 is going to be order epsilon to the power a half. Then in the limit epsilon goes to 0, this term goes to 0, this goes to 1, and this goes to 0. Now, distinguished limits demands that the terms we balance must dominate the rest of the terms in our equation. In this case, we can see that the terms we have balanced actually being dominated by the third term. So we're going to have to discard this value of alpha is half cannot give us our distinguished limit. Then next we balance term 1 and term 2. So in that case, 1 minus alpha must be equal to 0, because the power of alpha in term 2, power of epsilon in term 2 is 0. So that tells us that alpha must be equal to 1. Then in this case, term 1 is going to be of order 1, term 2 is going to be of order 1, and term 3 is going to be of order epsilon. Then as epsilon goes to 0, this goes to 1, this goes to 1, and this goes to 0. So this time the terms we balanced are dominating the third term. So this is giving us a distinguished limit. Okay, so we plug in alpha equals to 1 into the ODE. So our problem is now going to become dy dxi plus y is equals to epsilon times xi. Then we look for, now that we've done the rescaling, then we can in the rescaled system look for a regular perturbation solution. So we look for y equal to y naught epsilon y1 epsilon squared y2, etc., and substitute. So when we do that at order 1, we are going to get dy naught d epsilon plus y naught equal to 0 with that condition. Solving this is going to give us y naught is e to the minus xi. So if we solve this ODE subject to that condition there, at order epsilon, the ODE going to be dy1 dxi, y1 is equal to xi because of this term here. And then the condition on y1 when xi is 0 is going to be this one. So here, if we integrate this using integrating factor, so multiply both sides by e to the xi, And then if we integrate, the left hand side is going to be y1 e to the xi. This right hand side is going to be xi minus 1 e to the xi, and then there is going to be a constant, let's call it k. This process here is by integration, by parts. Just make sure you can work through that. And then when xi is 0, y1 is 0. So if we plug in here, this is going to give us minus 1 plus a is 0. So it tells us that a is equal to 1. Then when we rearrange, so this is telling us that y1 is actually going to be xi minus 1 plus e to the power of minus xi. Then at order epsilon to the power n, where n is 2 or bigger, we are going to get this equation as our governing equation, and this is going to be the condition. Now for all of these, when we solve, we are going to find that they give us 0. So that means the solution of the inner problem is complete. So y is equal to e to the minus xi plus epsilon xi minus 1 plus e to the minus xi. If we write this in terms of x, xi is x over epsilon, x over epsilon here, x over epsilon there. So this is going to be e to the minus x over epsilon plus x minus epsilon plus epsilon e to the minus x over epsilon. So rearranging, this is the same as x minus epsilon 1 plus epsilon e to the negative x over epsilon. There are two things worth noting here. The first one is that this solution, it actually contains the outer solution that we derived earlier. So you're going to recall that we found the outer solution to be x minus epsilon, so that is part of the solution. The other thing that is noteworthy is the fact that this solution is identical to the exact solution. So the solution is identical to the exact solution that was presented earlier. So that indicates that this method of asymptotic expansions is pretty okay.